V1 and E1 on this side, and then I have V2 and E2 on this side. I have wave function psi1 of x on this side. And then if I have a wave function psi2 of x on this side, what are the boundary conditions for the wave functions right at that junction? If you just stare at the Schrodinger equation, you need at least two boundary conditions at the interface. Just like what you did in your transmission line problem in ECE 350. You always need two boundary conditions. Like in the case of transmission line, is the continuity of the voltage and continuity of the current. Those are the two boundary conditions. In this case, what are the two boundary conditions that you need at this interface? This function cannot have infinity, right? This function cannot have infinity. That function, psi e of x of t, cannot look like this at the junction. It cannot look like that. Okay? You cannot have jump discontinuity. Because if it does have jump discontinuity, if you differentiate it one time, what will you get? You get infinity, right? And so this is not possible. So psi e of, on the left side, okay, we call this psi e1, psi e2. On the left side must be equal to psi e of 2 on the right side. Okay, this cannot happen, so it must be something like this at where the junction is. So this is one of the boundary conditions. Then the second boundary condition is that this cannot jump. This cannot jump. If it does jump, then if I differentiate, I get infinity again. So the second boundary condition must be 1 over me1 d dx of psi e1 must be equal to 1 over me2 d dx of psi e2. Okay, that's the second boundary condition, but the second boundary condition has the physical meaning. What is the physical meaning of the second boundary condition? The second boundary condition happens to have the physical meaning of the continuity of particle current. Okay, I didn't talk about the particle current once before. It turns out that the particle current is proportional to, if you go back to chapter 4 of your lecture note, the particle current is proportional to this quantity over here. Okay? And this particle current has to be continuous across the interface. If it's not continuous, then you're not conserving particle, or not conserving particle current at the interface. And in 1B, this simplifies to a normal derivative. Partial n means normal derivative. Okay? So then there should be the way you should write the effective mass Schrodinger in order to conserve particle current at interfaces. Okay, otherwise, if the divergence operator is here, if the mass is over there, then particle current is conserved. Are there any other questions? If not, then we move on to do something else. Because now we have an effective mass Schrodinger in a crystalline structure that can be giving us a simplified picture. We can study things like quantum wire. We can study things like quantum wire and quantum dots. Because we can fabricate them. Nanotechnology fabrication allows us to fabricate this kind of thing. And if you have the 2D structures going to the blackboard, and out of the blackboard, this is just the cross dimension, you have a quantum warp Okay, you have a quantum wall. You can fabricate this kind of thing by MBE, molecular beam epitaxial technology, or molecular beam epitaxy. Okay, where you can grow atomic layer by atomic layers. You can grow this kind of compound layer by layer, and then you can engineer them so that different layers will have different kind of compounds. And there's also, I think there's another one called MOCVD. I forgot what is some chemical vapor deposition molecule or something. I don't know what the O stands for.
Metal organic.
Metal organic, right?
Yeah.
Something. You can also grow this kind of thing. Okay. Those are the two competing technology. I think all of this came out of UIUC. Or the major players came out of UIUC. Okay, this is, I'm sure this was somebody UCSD, I think, somebody in the West Coast. Looking for this kind of. Or maybe not. Maybe somebody started it, but then it became very popular. I mean, popular by researchers at UIUC. So you can grow this in 2D. You can grow this in 3D. You can make the quantum wall into quantum wires by adding one more dimension. You can make them into dots by different kinds of nanofabrication technique. We can now study the behavior of an electron in these three kinds of devices. But then let's talk about density of states. Or DOS in these three kinds of devices. Okay. So let's talk about a bulk material first. If you have a bulk material, assuming that there's no scattering, ideal bulk material, then if we apply what is known as the periodic boundary condition, assuming that we have a plane wave propagating through a bulk material, we ignore the U part, the periodic function, the modulation part. This is just the block wave, the wave function part. And then we're going to assume that we have periodicity, okay, in this bulk material to make things simpler or countable. This might be my z-axis, this might be my, maybe I put my x-axis into the blackboard, y-axis, and then you might have L1, L2, and L3 for your three fourth dimension. And if you impose a periodic boundary condition, it means that the wave function repeats itself after the period of L1, L2, and L3. So if you do that, then this block wave can be approximated by e to the kx, which is 2 pi L1 x plus I 2 pi L2 y plus I 2 pi L3 z. Okay, can you see that this wave function repeats itself? If x is PL1, it becomes itself. If y is QL2, it becomes itself. If z is L3, it becomes itself, okay? Okay, so this wave functions repeat itself. That means if we start out with this phase over here, if it goes over there, it becomes itself. Okay, this is known as the periodic boundary condition. Periodic boundary condition. Why do we like to use periodic boundary condition? The reason why we want to use periodic boundary condition is because we can count the modes. Now we can count the kind of wave modes in the box, even though there will still be infinitely many of them. This should be an L1, I think. I can have an integer here as well, L2. L2 and then L3. Okay. Then my K vector can be written as L1 2 pi L1 A1 hat pointing in the x direction. Okay, this would be L2 2 pi over L2 hat plus L3 2 pi over L3 K3 hat. So my K vector is indexed by L1, L2, and L3. Capital L1, L2, and L3 are the sizes of the box, and they are not changing. But if you change L1, L2, and L3 as integer values, then the K vector represents a periodic way. Okay, of course your R can be just xa1 plus yk2 plus za3. And A1 hat, A2 hat, A3 hats are usual x hat, y hat, and z hat that you see in some other courses. Okay. So we can count the number of modes we can have in this box as a function of k, as a function of the length of k that we have, or as a function of the size of the box as well. And then we can count how many modes per interval of k. Okay, we can do this in 1D first. Let's assume that we reduce it to 1D problem. Okay. In 1D, we just have the wave propagating one dimension. Then k is just equal to L2 pi over L. Okay, and then we can write this as equal to L delta k in 1D, where delta k is 2 pi over L. So if you were to look at the number of modes we have as a function of k, we will have in one dimension, when L is 1, we have a mode. When L is 2, we have another mode. And L is 3, we have another mode. So 1, 2, this would be actually L equal to 1, 2, 3. So this is 2 pi. I can put this delta k. This is 2 delta k. This is 3 delta k. This will be 4 delta k. So these are the kind of modes I can have. These are the kind of block modes that I can have in one dimension. The density of states refers to how many modes I can have per unit k number or wave number. If I take a unit length of this k number, how many modes do I have over there? Okay. So I know the spacing of the mode. I know the spacing of the mode is delta k. If I take a unit value of the k wave number, then the number of modes that I have is 1 divided by delta k. This gives me the number of modes I have in 1D. And delta k is 2 pi over L, so it's L over 2 pi. So this is my delta k. Okay? But this is expressed in terms of the length of the box. I can normalize the thing by the length of the box, and then I can actually divide out the L. And in 2D, you can figure out, so this is the density of states in 1D, okay, as a function of k, because I'm actually plotting as a function of k is equal to L over 2 pi. And then if I repeat this exercise for 2D, kx, ky, and then if I have a 2D box instead of a 1D box, then the number of modes will appear to be something like this. You might have a 0 mode here. The number of modes I have will look something like this. Okay, it's periodic, so this is delta kx, this is delta ky. And you can figure out what delta kx and delta ky is. Delta kx is 2 pi over L 1. Delta ky is 2 pi over L 2. Okay? Then the density of states in 2D as a function of k is equal to the area, the unit area. Say this unit area is 1 by 1. Okay, 1 by 1 is 1 times 1 divided by the small area. The small area is delta kx, delta ky. So this is the density of states per unit area. And if you plug this in, this is equal to L1, L2 divided by 2 pi squared. Okay. And then you can repeat the count for 3D. For 3D, then is density of states in 3D is equal to L1, L2, L3 over 2 pi cubed. Okay, so these are different ways of counting the number of modes in a box that is 1D, 2D, or 3D. Okay, so this can be written as area of the box divided by 2 pi squared. This can be written as volume of the box divided by 2 pi cubed. Okay. And oftentimes people just divide this length, area, and volume out and say that this is the density of states per unit length. Okay, this just becomes 1 over 2 pi. It becomes the density of states per unit length of the box, and this will become a density of states per unit area of the box, and this will become the density of states per unit volume of the box. Okay. So this will have bearing on density of states of, say, a quantum wire, quantum wall, and quantum dots. Okay, they will have some relationship to them in this manner. Because if you have a 2D box, then it's like a quantum wall, because you make a quantum wall in 2 dimensions. And then in 3D, then it's like a quantum dot, and then for 1D, it's like a quantum wire kind of thing. But let's elaborate on this a bit more. Say, if we want to now find the density of states as a function of number of states per unit energy. Okay, these are density of states per unit wave number. We count how many states we have per unit wave number. What happens if we want to convert it into one that is per unit energy? So we do this by a change of variable. Okay, so it must be that if I were to multiply this by dE, this must be equal to the density of states per unit wave number times dk, dE dk. Okay? So what I need to do then is that in order to convert this, I must have the fact that the density of states per unit energy must be equal to the density of states per unit wave number times dE dk, right? Let me see, does this sound right? This doesn't sound right. So doesn't sound right. So I will have to multiply, if I want to convert the density of states from.
This reverse DE over DK.
What is that?
I mean, density of states in energy space is like you just differentiate the density in K space with respect to energy. So it's like the right hand side.
Okay, it should be the other way around. Okay, dk, dE, dE. Then I can say that these two must be the same. Okay, so correct. So the density of states per unit energy must be the density of states per unit wave number times dk dE. Okay, these two must be equal to each other. Okay. And then you can do the same thing to the other thing too. Like, so if you have in 3D the density of states in 3D per unit energy times this dE will give you the number of states in this energy interval. Okay. And then you can say that in this energy interval, okay, it would be given by the let me see how to say this in a proper way. That the number of states you have in this energy E, if you were to plot this in 3D, Kx, Ky, Kz, then the density of states, when the number of states is distributed in the lattice fashion, in the reciprocal lattice space. Okay. And then dE means change the frequency of the wave vector. If you were to change the frequency of this wave vector, okay, this K is omega over C. If you change the length of the K vector, it's like changing the energy. Changing the energy is like changing the radius of a sphere in K space. Okay. So if you change the energy, it's like mapping out a shell in this K space, and then that shell has a volume that is given by, so I can write down the density of states in 3D as a function of K times 4 pi K squared dk. Okay, this would be the number of states I have in this shell. Okay, and then I will have 2 states per unit point because I can have a spin up, spin down electron. So I have to multiply by the state of 2. And then I can change this as I did before and write this as 3dk 4 pi k squared dk dE times dE. So this must be g of 3D as a function of E. So that's how you change from K space to E space. Okay. You take the 3D in K space, multiply by 4 pi K squared times delta K. That gives you the same volume in the shell. Okay. And then multiply by 2 by taking into account of the fact that you have 2 electrons per state. And then you will have this formula. Okay, that G3dE is equal to 8 pi G3dK K squared dk dE. Okay. So, but then for the effective mass Schrodinger, okay, I know that E and B are related, E and K are related by this equation. That's how E and K are related. So from this I can find the E dk. It's h squared K over ME. Okay? And then you find that K is equal to E minus B over 2ME over B. Okay, from this you can find K. You can plug in the second one, you will get dk dE is equal to ME over 2H squared over E minus B. And then you can work out your 3D, the 3D density of states. It will look something like this: 2 pi squared 2ME over H squared 3½ E minus B half. Okay, so the density of states in 3D bulk material will look something like this, and if you would plot this as a function of E, it will look something like this. Okay, this is B. B larger than B gives me that kind of. Okay, this is correct. Let's take a 5 minutes break and come back. We'll talk about. It seems that I need more than that, more time than 1 hour.
That's okay.
Okay, so are there any questions before we take a break?
What's the lowest square root of 2ME? The denominator?
ME 2H squared, right?
The one above that. There's this character I can't read. It's
2ME over B, right?
oh, it's on. It's the number 8.
Sorry. Let me see what I have. This part. Sorry. This part. Okay. Yeah, so this gives you the density of states in the bulk material. And we'll come back and look at the other ones. Yes?
I'm just curious, like, we have this kind of periodic boundary conditions,
Right.
and we also have those lattice structure
Right.
periodic
Right.
boundary conditions.
Right.
So just are they somehow related?
These are much bigger than the other one. The other one was on the order of lattice spacing when we studied the block locate theorem. Those boundary conditions are on the order of lattice spacing. So UP was periodic function on the order of lattice spacing. This is a periodic boundary condition on the order of the size of the bulk material. Say you have this 100 nanometer device or 1,000 nanometer device. This would be on the order of that spacing. Much larger than the lattice spacing. Lattice spacing might be 1 nanometer or something less than that. Okay, so those two are very different numbers.
Then how do we make this boundary material to be periodic? So it's like you put another dot.
Right. So I guess you're worrying about a little bit of mismatch there, right? But you don't have to. I guess we have already homogenized this. We assume that effective mass and effective potential are all smooth. We start out with the periodic thing, then we replace it with this, which is smooth. And we have those effective mass, which is essentially a smooth function. So we are under effective mass and effective potential approximation in this picture. So you don't have to worry about lattice mismatch when you discuss this. Right? Okay? So if no question, we take a 5 minutes break. It seems I need more than 1 hour to finish my lecture. So we take a 5 minutes break.